Section 10.5 is equations of lines and planes. So first we'll introduce lines in 3 dimensions, then we'll see equations of planes in 3 dimensions. So a line is determined by its direction and a point on the line. So the direction is given by a vector v, and the point on the line sort of places that line with its direction in the 3-dimensional space. And that's all we need to determine a line. It's kind of similar to slope and a point on the line for point-slope form in 2 dimensions. The standard form of the equation will look like this. R is some variable composed of x, y, z equals r naught, our point, composed of x naught, y naught, z naught, plus t, a parameter or free variable, times v, a vector a, b, and c, that's our direction vector, kind of like our slope for 3 dimensions. So that's the anatomy of a line in 3 dimensions. If we decompose this expression into its constituent components, then we'll have this set of parametric equations parametrized by a value t, which takes on any real number in the set of real numbers. Okay, so that's the background definition. Let's see this in practice. So first example is pretty straightforward. They ask us to find a vector equation and parametric equations to the line through the point 6, negative 5, 2. So we have a point, and parallel to the vector, we have a direction, 1, 3, negative 2/3. Using the formula from the previous page, we see that r is equal to r naught plus v times t. Now we have the point vectorized, so all we need to do is put that point into a vector notation, and that'll suffice for r naught. And then we have ABC, or the vector v, the direction, times t. And remember that that's equal to our free variable vector r. So it represents any point on this line through the point 6, negative 5, 2 with the direction 1, 3, negative 2/3. Now, expanding this, 6 plus 1 times t, negative 5 plus 3 times t, 2 minus 2/3 t is each of these expressions here, and these are the x, y, and z components of this variable r, expression for r. So that's our parametric equations linked to the vector equation for the equation of a line. Pretty easy transfer to go in and out of those. Another way that we can represent a line is through its direction numbers, which will give us the symmetric equations. The direction numbers are exactly these values right here. A is the direction number in the x component, B is the direction number in the y, C is the direction number in the z component. And if we solve for t, like we would often do in parametric equations, here I'm doing it off to the side, for x equals x naught plus at and y equals y naught plus bt, solving for t in each of those equations gives us x minus x naught over a equals t, and y minus y naught over b equals t. They're both equal to t, so they're both equal to each other, and that forms this equation right here. Do something similar to get z minus z naught over c, and we get this set of symmetric equations. They're symmetric because they're all equal to each other. If it so happens that one of the direction numbers in one of these variables is 0, for instance a equals 0, then x is just equal to x naught. It doesn't fit in with the symmetric equations, but we write it off to the side. It's fixed at some value because its direction value is 0, so it never changes as t changes. Okay, so to see this in practice, we're asked to find parametric and symmetric equations for the line through the origin and through the point 4, 3, negative 1. So the first thing we need to do, perhaps, is to find the vector v, the direction vector that passes through both of these points. If we're given 2 points, we can determine the direction via the vector connecting the 2 points together. It doesn't matter which direction we point, we'll still form the same line. So in this case, I've chosen 4, 3, negative 1, and then the origin at 0, 0, 0, and we'll use 4 minus 0 for the first components, 3 minus 0 for the second components, negative 1 minus 0 for the third components. We end up with the vector 4, 3, negative 1. Now, had we not had one point be the origin, this would look different from the given point. It won't always be one of the points, but it should be the difference of the 2 points. Since one point was the origin, it made this calculation simple, possibly a little confusing in the example. So now each of our parametric equations is given by x equals x naught plus our direction vector times t. So this calculation is actually doing the A, the direction number, B, that direction number, and C, this direction number within our parametric equations. This would skip the step that we did in red, so it's either way. We could do the step above and then fill it in, or we could just do it as we have it in the parametric equations. But once we simplify this line, we end up with our answer, or our parametric equations for the equation of this line. Solving for t in here, or in other words, eliminating the parameter, eliminate the parameter t, we get the symmetric equations below. Eliminate the parameter t. In other words, solve for t and then equate everything that's equal to t to each other, and we end up with the symmetric equations here. So that's a third way to represent a line in three-dimensional space. Notice that all these variables are occurring linear. There's no t squared showing up, x or y squared. Some of these things could come about with a parameterization, but we won't really do too much of that in this section. So it's nice that we're going to keep everything linear as we'd expect for a line. Now, connecting a line segment from R0 to R1 with a vector. Okay, so this is going to be a finite length line. That's reflected by the fact that t takes on values between 0 and 1 and no further. All right, so that'll keep us at a finite length. Now let's see how this equation actually works. When t is equal to 0, that shuts this one down. This part of the expression is now 0. We have 1 minus 0 here as a 1 times R0. So r of t is equal to R0 when t is 0. So we have a point at R0, which is what we want for this line segment. Now when t is equal to 1, this is 1 times R1, so it exists as R1 in the expression. This is 0, so R is equal to R1. So the other end of this line segment is at R1. So it's a nice intuition for how this formula works. All the values in between 0 and 1 fill in the rest of that line segment. Okay, so to execute this formula is pretty straightforward. We're asked to find a vector equation for the line segment between these two vectors. Well, we have 1 minus t times one of the vectors plus t times the other vector. Doesn't really matter which order we pick for these, we'll still end up with a line segment that runs from one to the other. If we switch the placement of these, then we're just switching the direction in which the line connects one point to the other, because we're switching the direction from 0 to 1 to 1 to 0. Okay, and this is the result of that vector equation here. One thing that we should say at the very end of this, to be clear, that's an infinite length line without qualifying the fact that t needs to be between 0 and 1. So this really should be part of our answer to make it complete. Okay, but it was more or less understood in the problem. So that's a line segment. Next up is the most complicated thing we'll do with lines in this section, and that is to determine whether two lines are parallel, skew, or intersecting in three-dimensional space. We're given two lines in this example, line 1 and line 2. One parameterized by t, one parameterized by s. Both of those will range over all real numbers unless we're otherwise told. We're not otherwise told, so t and s take on any real number value. So let's put our lines in vector form. That's the first thing to do. So all of our directions, or all of our points for R1, 5, 3, 1, make up that R0 vector. Our direction vector, negative 12, 9, 3. Directions, essentially kind of the slopes of these linear equations. And we've got that. And similarly for R2, we get L2, the second line. Now, before we move too much further, what does it mean for two lines to be skew? Parallel should be obvious. The two lines never intersect and they have the same direction. Okay, we'll get to that in just a moment. So that means that the direction vectors are either equal or they're off by a scalar multiple. But we have a nice check from section 10.4 to determine whether or not two vectors are parallel. If the direction vectors of two lines are parallel, then the two lines must be parallel. Skew, though. Skew is this. Imagine we have two lines in 3 space. This blue line is above the red line, which is within or below the page. Right? We can think of it like that. We're looking down at where these lines could potentially cross each other. They're crossing without actually intersecting, without actually sharing a point in common. So that's a skew line. Okay. So now we'll know that if a line isn't parallel or intersecting, it must then be, or pair of lines isn't parallel or intersecting, then they must be skew to each other. So to check parallel, to get back to that, we have this identity from section 10.4. You take the cross product of these two vectors. If it's equal to 0, then the two vectors are parallel. If the two vectors are parallel, then the two lines are parallel. So once we carry out the details of this cross product, remember using this diagonal method or however you expand this determinant. Some of the details are included here. We find that we get a vector that it's not 0. So since it's not 0, we conclude that the direction vectors of these two lines are not parallel, thus the lines are not parallel. Had they been parallel, we'd be done, our work would be complete, and we'd say that the two lines are parallel, and that's the end of that problem. But since they're not, we have to go on and check to see whether or not they're intersecting. If they're not intersecting, then they must be skew. So to check intersecting, what we want to do is set these two lines equal to each other to see if values of t and s, which would arise from these two lines being set equal to each other, actually exist. When we set these two things equal to each other, we get a system of equations for the x components here, for the y components here, and for the z components here. Okay? So that's 3 equations with 2 unknowns. Now we can pick any 2 of these equations and solve for the 2 unknowns t and s. What we're hoping to see is that these equations have a solution for t and s. If we get a solution from this system of equations, then what we want to do is go back to the third equation. We used the first 2 equations, by the way, in this case. If we get a solution that works from this system, then we want to take it back and make sure it works for the third equation. If that's the case, then these lines intersect. Well, in solving this system of equations, what happened was we ended up at 0 equals -6. We multiplied this equation by 4/3 to get a common 12t, so we could cancel this, eliminate this variable, and in doing so, that eliminated this s variable as well, sort of coincidentally, and we ended up with 0 equals -6. That's an inconsistency, or it's a contradiction. And if we arrive at something like that that doesn't make sense, well, that tells us that these 2 equations are inconsistent, which means that they don't have a solution, so that this equation can't hold to begin with. So that means the lines don't intersect, and we conclude that the lines are skew. Okay, so it's just essentially systems of equations for intersectional lines. For parallel lines, we can use this cross product identity to check that it's equal to 0 or not. In this case, neither of them held or checked out, so we conclude that the lines are skew. In the next video, we'll talk about planes.